After we've conducted the one-way ANOVA test, which tells us to reject the null, meaning not all the population means are equal, we can conduct the Tukey-Kramer test to see which means differ. Here's the formula we will use to set up the critical range for each pair of means that we're comparing. First, we have our Q value, which is the value from Appendix I. And in order to get Q, we'll need our degrees of freedom, which is just K, which is the number of populations we're examining, and the degrees of freedom for within samples. So that was our N sub T minus K. We also need to plug in our MSW, which is our mean square within that we get from Excel. We'll divide that by 2. And then for our N's here, depending on which two pairs of means that we're examining, we will plug in the sample sizes for those means. The Tukey-Kramer test allows us to compare the confidence intervals of our groups. Specifically, we compare 2 at a time, hence it's a pairwise comparison. Now note we study confidence intervals and not an exact value because we have sampling error that we have to account for. So remember in Chapter 8 when we learned about confidence intervals where we believe our mean is somewhere between two numbers, we create these intervals so that it accounts for the sampling error or the variation that we might see between samples. So in this example here visually, we can see that 2 of our population means are equal or the same, including their confidence interval. And then 1 is different from the other 2. So let's continue with our homework problem of number 13. We've already determined that not all of our sample means for the 4 kinds of emergency lights are the same, but we don't know which ones are different. So we'll use the Tukey-Kramer test to compare them. So part B asks, if the test conducted in part A turns out that our null hypothesis is rejected, which manufacturer should we use to supply the lights? Can we eliminate one or more manufacturers based on our data? So we're going to conduct the Tukey-Kramer test using an alpha level of 0.01 for multiple comparisons. So here's the decision rule. If the absolute value, or the distance between our 2 sample means, is greater than the critical range, here's my greater than, here's the formula for my critical range, we can conclude that our means do not equal each other. To get our critical range, we need to use the MSW, or mean square within, that we got from Excel. So that was the 6,518.125, if you go back and check your Excel output. For the Q value that we need to get in Appendix I, we use the degrees of freedom, our first one being K, so how many populations are we looking at? 4. And our second degrees of freedom is our N sub T, or our total sum of sample sizes minus the number of populations or groups we're studying. So that's 16 minus 4, and that gives us 12. And then our P is 1 minus the alpha in our story. So our alpha was 0.01, so subtracting from 1, we get 0.99. Now be careful with the P because this will determine which page of the Appendix I that you're going to use. So here's a snapshot of when P equals 0.99. And again, we know that because to get our P, we take 1 minus alpha, and our alpha was 0.01. So that gives me the P at 0.99, so I'm looking at the correct page, the correct table in Appendix I. Then we need to find the first degrees of freedom. Recall that it's simply K, and that will be our 4 groups that we're comparing, the 4 manufacturers. And this is at the top. We're looking at the column for 4. So we're going to look for our second degrees of freedom here. We're going to just look down here on the left, where we take our total sample sizes minus the number of populations we're studying. So that gave us 12. And so when I go look at column 4 and row 12, our Q value is 5.5. So recall in our ANOVA output, we got this summary table right here. And this is what we're actually going to be using to conduct the Tukey-Kramer test. Specifically, we're going to be looking at the sample means, or the average time in hours for our emergency lights for each manufacturer. So bringing it to our slides, because it's easier to see. So here's the formula for critical range, and I'm going to go ahead and plug in our variables. The Q value we obtain from Appendix I, our MSW, and our sample sizes here in the count that we're going to plug in. And we only need to calculate one critical range because all of our samples had the same sample size. So plugging in the numbers, we will then use our calculator to find the critical range. I always recommend working in our parentheses first and then multiplying it by the numbers just outside of it, then square rooting the entire thing, and then multiplying it by 5.5. That should give you a critical range of 222.02. So now what we have to do is we're going to do a pairwise comparison. So I'm going to compare two groups at a time. I will compare type A and type B's average time in hours against the critical range. And then I'll do that for each pair of manufacturers. So looking at our table, if I compare type A and type B, I would take the absolute difference of the average time in hours. And that gives me 231.5. And I do the same when I compare type A versus type C, type A versus type D, type B versus C, B versus D, and C versus D. This is similar to when in chapter 4 when we were working with probabilities and we were looking at all the different combinations. So in this case, we are doing all the different combinations of how we could compare our manufacturers two at a time. And we take the absolute difference to see how far apart our two manufacturers' average hours for each emergency light is. After we've calculated the absolute difference, we'll now have to compare it against the critical range we calculated up here in the formula. So looking at type A versus B, 231.5, how does it compare to our critical range of 222.02? It's greater than. Because it's greater than, it is significantly different. When we look at A versus C, our absolute difference of our means is 54.25. That's less than our critical range. That means they are not significantly different. When I look at A versus D, my 75.75 hours is less than our critical range, so it's not statistically significant. Comparing emergency lights B versus C, 177.25 is less than our critical range, so it's not significant either. When I compare type B versus type D, our absolute difference is 307.25, which is greater than our critical range, and therefore is significantly different. And then our last pair, when I compare our emergency lights from manufacturers C versus D, we get 130, which is less than our critical range, and that means it is not significant. After we compare each pair of manufacturers, we can see that only two stand out. When we compared A and B, was significantly different than the critical range, as well as our type B versus type D was also significantly different in the critical range. So we need to make note of this because now we have to interpret what it means. What I recommend is we first rank order our light bulbs from highest to lowest. When we reorder our emergency lights, type B is the highest at 1,335.75 hours, and then followed by type C, then type A, then type D. Now we might say, well, just looking at these numbers, why do I have to do this comparison? Type B has the highest number of hours. That means it lasts the longest. Why wouldn't we just award to type B? We cannot simply look at the sample means and say this, because these are just samples. We have to account for sampling error. Hence, we had to apply the critical range process earlier. Recall that if we exceed the critical range, that means our pairs are significantly different. So which pairs are significantly different from each other based on the critical range? Recall in the last slide, we only found two sets of pairs that were very different from each other. We now need to examine those pairs closely. So we found that type A versus B and type B versus D were very different. So looking at our data, type A had 1,104.25 hours versus type B, which had 1,335.75 hours. So looking at this, we can see that type B lasts longer than type A. And then in the second pair, that was found to be significantly different. So again, we can see that type B lasts longer than type D. That means we can reject manufacturers of type A and type D because both of them are significantly lower than type B. So our conclusion based on the Tukey-Kramer test is that we can eliminate type A and type D because their mean life is significantly less than type B. Now you might say, well, can't I also eliminate type C because When I look at the means, it looks smaller than type B. However, we cannot eliminate type C because when we did our Tukey-Kramer test and compared B versus C, it was not significantly different, meaning our absolute difference was not greater than the critical range. Just because the sample from type B is higher than type C, it's not enough evidence because after we account for the sampling error and apply the critical range, it was not significantly different. So in an organization, like when I worked at UCSD, we would continue evaluating the type B and type C bulbs. Perhaps we will do more testing. Having worked in the public sector, bidders on projects often sue if they feel that they've been unfairly rejected on a project. So with this test, if type A and type D manufacturers wanted to protest the bid, we have evidence to show that they lost because their emergency lights do not last as long as type B, even accounting for sampling error. We do not have enough evidence to eliminate type C. And if we did, just by comparing the sample means and not accounting for sampling error, they could protest it and we would lose the lawsuit and have to include them back in the bid process to include additional testing for our emergency lights. Or worse, we'd have to pay out on the lawsuit. So that's why I like this example so much because it has real-world applications. So if you have any questions, just let me know.